You know, we've all had that moment, that spark of awe watching a reinforcement learning agent do something that feels, well, superhuman. It really makes you feel like we're right on the edge of true AI. But then we try to take that same magic and bring it into the real world. And so often it just breaks. Why is that? Well, that's the puzzle we're going to unravel together today. I mean, think about it. RL agents have eaten the best Go players on the planet, a game with more moves than atoms in the universe. They've coordinated with godlike precision in Dota 2. So, why is a task that seems so much simpler, like a robot arm trying to pick up a new object, still such a huge, monumental challenge? And if you're a student, or if you're a practitioner out in the field, you've definitely felt this. There's this frustrating gap between the beautiful, elegant theories you read about in a textbook and the messy, unpredictable, and frankly often expensive reality of getting RL to work on a physical system. The promise is absolutely there, but the path to get there is just full of these hidden traps. Okay, so let's really dive into this. To understand why real-world RL is so incredibly hard, we're going to start in the idealized clean room of pure theory. And then, one by one, we're going to add the layers of chaos that reality loves to throw at us. So in its purest form, the reinforcement learning loop, it's just beautiful. You've got an agent, that's your algorithm. It looks at a state from its environment, it takes an action, and then it gets a reward or penalty. And it just does this over and over, millions, sometimes billions of times, slowly learning the absolute best strategy. It's a perfect feedback loop, especially when you're in a simulated world where time and trials are, for all practical purposes, completely free. All right, here comes our first dose of reality. What happens when you leave that simulation and move to a physical robot? Suddenly, every single action costs you something. It costs time, it costs energy, it causes physical wear and tear. You can't just run a billion trials anymore. You have to learn, and you have to learn fast. And that brings us to our very first major challenge, sample efficiency. You see, unlike a game where an agent can play against itself for what amounts to centuries of simulated time, a physical system might only give you, say, a few thousand chances to get it right. Your algorithm has to be incredibly efficient, squeezing every last drop of learning out of every single interaction. Okay, so not only is every try expensive, but what if some of those very few tries could be catastrophic? In a video game, the worst thing that happens is you lose, you see a game over screen. But in the real world, one wrong exploratory action could mean a multi-million-dollar robot arm smashing itself into a table, or a chemical process going critical, or an autonomous vehicle making a truly dangerous move. This introduces this absolutely critical need for safety constraints. It's not good enough to just maximize the reward. The agent also has to learn to never violate certain hard rules. Researchers actually formalize this with something called a constrained Markov decision process, or a CMDP. You can think of it like this. The goal is still to get the highest score possible, but you have to do it while staying under a really strict safety budget for any bad actions. You can't just win. You have to win safely. So, our agent has to be efficient, and it has to be safe. But what happens when the environment itself doesn't stay the same? What if the very rules of the game start to shift while our agent is in the middle of playing? This is the challenge of what we call non-stationarity. A core assumption in a lot of basic RL is that the physics of the environment are fixed. But in the real world, a pump's efficiency slowly degrades over time, a robot's joints wear down, the preferences of users in a recommender system just drift. So a policy that was optimal yesterday might be totally inefficient or even dangerous today. The agent has to be able to adapt on the fly. And now for the last and maybe the most common layer of real-world messiness. In a lot of high-stakes industrial settings, you can't just let a brand new, untrained agent take control of a live system. It's just way too risky. So how are you supposed to train it when all you have is a log of data from the old, probably suboptimal controller that was running before? This forces us into what's known as offline or off-policy training. Offline just means we're using a fixed historical log of data. Off policy is the really key idea here. Our new agent has to learn by watching the actions of an old policy, that old controller. It's kind of like a rookie quarterback learning not by playing in a game, but by studying game tapes of a retired veteran. They have to figure out a better strategy just by analyzing what happened before without ever getting to step onto the field themselves. So when you're faced with all these challenges, a really common intuition, especially if you come from the world of supervised learning, is to just use a simulator. right? Train the agent in a perfect, safe, simulated world with basically infinite data, and then just transfer it to the real world. But this leads to a really seductive trap. In supervised learning, let's say image classification, more data is almost always better. It helps the model generalize. But in RL, that intuition can be really misleading. Training for billions of steps in a simulator doesn't guarantee success in the real world. In fact, it can create a really brittle agent that is over-optimized for a world that doesn't actually exist. And this gets to the heart of the problem, what we call the sim-to-real gap. No matter how good your simulator is, its model of the world, let's call it MSim, is only ever an approximation. The real world, MReal, has all these subtle complexities, friction, air resistance, noise, things that are nearly impossible to capture perfectly. So an agent trained only in MSim is often completely and totally lost the first time it encounters MReal.
So, if we can't build a perfect simulation, what do? We have to change the goal. Instead of training an agent that's perfect for one single idealized environment, we need to train an agent that is robust enough to handle any environment it might reasonably encounter.
And the key insight, the way we actually get there, is with a beautifully simple but incredibly powerful concept. We have to embrace entropy. Now, in physics, entropy is a measure of disorder. In RL, we can think of it as a measure of curiosity. Algorithms like soft actor critic, or SAC, actually change the agent's goal. Instead of just maximize rewards, the new goal becomes maximize rewards plus entropy. It's like telling the agent, yeah, find the best path, but I'm also going to give you bonus points for trying out different unpredictable moves along the way. This bonus for randomness stops the agent from finding one single perfect solution and just exploiting it forever. Instead, it's forced to develop a much wider, more adaptable set of skills, and that's what makes it robust to changes it's never seen before. Now, what's really cool is seeing how this idea of building robust, adaptable agents actually plays out in real applications. Let's take a look at a couple of quick examples. So in a recent study on robotic grasping, researchers compared two really popular algorithms: PPO, which is more focused on just stable policy improvement, and SAC, our entropy-loving algorithm. And as you can see here, in a dynamic environment where the object's properties were being randomized, SAC actually got a higher success rate for both grasping the object and the tasks that came after. Its built-in drive for exploration just made it more robust to all the variations in that simulated world. Another brilliant example is OpenAI 5. To play Dota 2, the agent has to process this massive, incredibly complex observation space you can see a piece of here. I mean, everything from the minimap to the status of all the heroes and items. But the real challenge is that Dota 2 is constantly being updated with balance patches, a perfect example of a non-stationary environment. So instead of retraining from scratch every time, the team adapted to these changing rules with a really clever technique they called surgery, where they would carefully modify the agent's neural network to account for new game mechanics without losing all its previously learned skills. So, after diving into all of this, what are the crucial takeaways? If you're out there trying to apply RL in the real world, here are 3 mental models that can really help guide you. First, expect messiness. The real world is not a clean room. Just assume from the very beginning that you're going to have to deal with safety constraints, delays, and incomplete information. Second, bridge the gap with chaos. Don't try to make your simulation a perfect one-to-one copy of reality. Instead, use techniques like domain randomization to make the simulation even more chaotic and varied than the real world. This actually forces the agent to learn a truly generalizable policy. And finally, aim for robustness, not perfection. Your goal is not to find the one single best path. It's to build an adaptable agent that has many good options in its back pocket. Use entropy, encourage exploration, and you'll get there. And all of this brings us to a final, really crucial thought. Solving these technical challenges is just one part of the puzzle. As we get better and better at creating these robust, autonomous agents that operate out in the real world, we're faced with an even bigger question. It's no longer just about performance. It's about safety, it's about explainability, and ultimately, it's about societal trust. The next frontier isn't just about making it work. It's about making it trustworthy.